Welcome to another episode of AI with Sally, an EE Times podcast that brings you inside my conversations with luminaries of the AI chip industry. Today's episode is brought to you by our sponsor, SiFive. In this episode, we're joined by John Simpson, Senior Principal Architect at SiFive. John works on SiFive's intelligence product line, which is their RISC-V processors designed for AI workloads for the range of applications from the edge through to the data center. I learned a lot asking John about vector and matrix architectures, memory systems, and how RISC-V can support modern machine learning workloads. In this conversation, we'll dig into the architectural trade-offs behind vector-length-agnostic design, matrix multiply acceleration, memory latency hiding, and how SiFive is contributing to the evolving RISC-V matmul standards. Here's my conversation with John. John, welcome to the show.
Hey, thank you for having me here, Sally.
So, John, you're Senior Principal Architect for SiFive's intelligence products. Perhaps you could just set the scene for us a little bit. What is this line, and tell us a bit about how it fits into SiFive's portfolio?
Yeah. SiFive's been around for 10 years now. So SiFive has three product portfolio ranges. The Essential range, that's our small in-order processors. They could be microcontrollers all the way up to Linux-capable devices. At the high end, we have our Performance series. So that's out-of-order superscalar processors. And then what I work on is the Intelligence family that sits between those. It's basically we take the Essentials and we add vector units onto the Essential processors, and that gives us the capability to do lots of number crunching.
So I think when we spoke before, you mentioned that with the intelligence line there, it kind of covers quite a big range of applications, all the way from edge, even far edge, all the way up to the big kind of data center computers or big supercomputers. You know, how do you think about scaling an architecture across all of those different applications? Is that even possible?
Yeah, well, we're claiming it's possible. We certainly have the range on the Intelligence family. From X160 is a 32-bit RISC architecture with vectors. They're narrow vectors. The vector width's 128 bits. All the way up at the high end, we have XM, which is our largest intelligence product. It is actually 4 wide vector processors with a matrix engine attached to them, and that would be what we target towards the data center. Yeah, but fundamentally, we're solving the same problem. We're doing number crunching. We're performing mathematical operations. So even at the far edge, where you need some acceleration, narrow vectors are useful. In the data center, where you have more data to crunch, the vectors get wider and wider. We put more vector units down. We put multiple processors down, and then eventually we have the matrix units. So it's all about how much area do you have, or can you afford to do this number crunching? And then the other thing that has to scale as well is the bandwidth. You have to feed the engine. It's no point just putting big engines down if you can't feed them. So the data bandwidth has to scale up as well. And at the high end, we have a terabyte a second of data bandwidth that's available.
I was going to ask you about code portability as well. With scaling between these different applications, is there any benefit to, well, first of all, can I use the same code with the different members of the intelligence family? And secondly, would I even want to do that, to be honest?
Yeah. So it's possible, but that's not guaranteed. So at the low end, like I said, it's a 32-bit RISC-V architecture. So if you start off with a 32-bit ISA, 64-bit instructions are just not going to work. So no, in that case. And at the high end, if you're using the matrix instructions, then those matrix instructions don't work at the low end. So no, it's not a single ISA all the way through, but it is possible to take vector instructions and have them work. So if you pick a particular 64-bit vector ISA, RISC-V vector standard, those instructions are scalable. RISC-V vectors are known as vector-length-agnostic, and so we can have implementations that are 512-bit vectors or 1024-bit vectors, and it doesn't matter. The same instructions in those implementations will work as long as the underlying architecture, RISC-V architecture, is the same. So in that case, it's RV64, and we're not using the matrix extensions. In that case, yes, they do scale, and you can run the same code at the edge and in the data center. That is certainly possible, and that is useful. There are use case scenarios, industrial use case scenarios, where you want to do some sort of edge inference applications, but you also want to be able to fall back to a data center, a cloud backup. Maybe you're doing incremental training back in the data center, or there are some edge cases that the units at the edge, they just can't handle it. It's something they don't recognize, and it goes back to the cloud. So there are uses, certainly, where running the same code in the data center and at the edge is useful, yes.
There are some cases, okay. Overall, I mean, I know you're saying this is specifically for AI, but
it's not specifically for AI. I'll step in. I'll step on.
Okay, yeah, please.
Yeah. So no, there's number crunching all over the place. It's not AI. Just happens to have a lot of numbers that need to be crunched, but there are use cases all over the place. Audio processing, famously, so DSPs in the past do a lot of audio processing. There's number crunching there, so it's suitable for that type of work. There are lots and lots of use cases where data needs to be processed. So these intelligence processors, that's what they're all about. It's moving data in, crunching the data. They work as application processors, so you can certainly run RVA23 is supported on the 64-bit ones. So they could run as an application processor, but they're in order. So the out-of-order performance series is a better application processor, but when it comes to number crunching, any type of number crunching, these are great processors, yeah.
So anything where you've got more number crunching than you could do on a CPU, or why wouldn't I use a GPU? It's just application dependent, right?
You can use a GPU, but it's potentially a different ISA than your CPU. So if you're happy to mix ISAs, go for it. This is one ISA for your CPU and number crunching. So CPUs have done this in the past. They've introduced SIMD in the past, so single instruction, multiple data. The RISC-V approach is vectors. It's slightly different, similar concept that we're trying to crunch multiple pieces of data with a single instruction. So SIMD in that sense, but unlike SIMD, it's not a fixed length. So traditional SIMD came out 256-bit, 512-bit. RISC-V, like I said, is vector-length-agnostic. So you can have implementations of any vector length to be V compliant. It's 128-bit minimum, all the way up to 64K-bit maximum. So there's a wide range there of possible values. The other thing you can do with vectors that SIMD doesn't traditionally do is you can gang up vector registers. So the vector ISA has 32 vector registers, but you can gang them up. You can say, I actually want to work on 2, 4, or 8 of these registers together with one instruction. And that makes the virtual vector register even longer. So you're getting even more number crunching per instruction. And then the other difference with the vector ISA is that you don't specify the operand size in the instruction. So with traditional SIMD, you would say, I want to do a signed add of 8 bits, or I want to do a signed add of 16 bits. With the RISC-V vector, you don't do that. You just say, I want to do a signed integer add. How many bits? Well, there's a control register that you set up ahead of time that sets the operand width, and it could be 8, 16, 32, or 64-bit operands. But the instruction doesn't encode that. So you can have the same code operate on different operand widths, and the control register ahead of time is set up. So you can try different algorithms, different precisions if you want it to in the floating point world, or in the fixed point world. You can try different precision algorithms with the same code, which is quite unusual as well.
I think, as we mentioned, my understanding is that edge hardware is more likely to use the shorter vector lengths, but then in the data center, I guess vector lengths can be much longer. I was hoping you could talk us through a little bit about the trade-off between longer vector length and PPA.
Oh, that's a really complicated subject. So,
okay, sorry.
So firstly, if I look at data center, sometimes in the data center, in that application, people want to go out of order. And I would recommend you don't use wide vectors when you go out of order. So in fact, it's just the size of the the reservation stations, the out of order hardware, you don't want to have a lot of that hardware for wide vectors. If your vector lengths are 1,000 bits, that's a lot of hardware to support out of order operations. And then the other thing you might not want to do with wide vectors is perform speculative operations on them because of the energy you're wasting. If you misspeculate it, if you took a wrong branch, you really don't want to be wasting that energy. That is a lot of wasted power. So yes, if the data center it will accept in-order processing of number crunching, then absolutely wide vectors is the way to go. So wide vectors are great for when there are conditions that are easy to predict. So AI is a great example of that. The models, I know exactly today, give me a model and I know what I'm going to execute on that model. There's no need to ever have a branch mispredict. Now, in the intelligence processors, we actually avoid the problem altogether. We put the vector unit after the commit point. So it's a backward processor. We commit the instructions before we even execute them. So there's never a chance of a branch mispredict in our intelligence processors. So we don't have any of that wasted energy whatsoever. There's none of this rewind the instruction, try and recover state that we need back again because of a mispredict. We don't have any of those issues at all. So yes, in the data center, wider can be supported. You certainly want to be crunching more data. So like I said, it's complicated. The first thing you do is, well, you're going to have to feed the data in. So the first thing you actually have to solve is getting the data in. And so we have very wide data paths for our load units to be able to get the data into the processor. Then if I take one of our processors, the X390, its vector length is 1,024 bits. But we actually implement a scheme called DLAN, where DLAN is half of VLAN. The data path width of the implementation is half of the vector register width. So we implement half of a ALU, think of it that way. And it would take 2 beats for us to execute a single vector instruction if LMOL is 1. If we haven't ganged those vector registers together, if we have ganged them together, it's going to take us even more beats than that. So yeah, so that's the first thing we do. So we save area by only having this half width vector ALU. And then we add a second vector ALU, but it doesn't perform all the instructions. It does the most common instructions like adds, subtracts, multiply, adds, but it doesn't do the infrequent operations, divides and square roots and such like. And so the area of that second vector ALU is only 40% of the area of the first. And so in terms of unit area, instead of 1 + 1, 2 units of area, we have 1 + 0.4. We have 1.4 units of area in our vector ALUs. And so we're still getting 1,024-bit effective throughput from the 2 vector ALUs, but the area, the total area is only 70% of what it would otherwise be. So we've made significant savings in that regard. And then for some other operations that are even more infrequent, we can throttle that back even more. So one thing we have throttled back, for instance, would be the 64-bit throughput. There are many rules and regulations about exporting vector supercomputers around the world. And so we reduce, by default, the vector throughput for 64-bit arithmetic down to 1 element per cycle. So that's crippled. Naturally, we could do more, but we've crippled it down. And that saves even more area again. So we're saving even additional area for those particular data types. What else do? We give our customers the option to configure certain things. They can configure the support that they want. Do they want the full vector ISA? Do they want the SiFive proprietary extensions? We have lots of extensions to accelerate certain functions for different workloads. Do they need those? Do they not need those? They can have them or not. And then the other thing that we'll hopefully get into in a bit is we have queues that enable us to hide external memory latency, and the customer can configure the depth of those queues if their external memory is really close and they don't have a lot of latency to hide. We can make those queues much smaller, saving all the area. And if they have lots of external memory latency that they're trying to hide, then those queues are naturally going to be deeper and they have more area. So there's lots of things that you can do. You can configure these things like crazy.
So with the vector length, it seems like you pretty much always have to chop up the vectors, chop up the data, or chop it up. There's no synergy between the vector length and the actual size of the data that's coming in. Am I getting this right? How do you approach kind of chopping up the data versus we spoke about the data path width versus the vector width, but how do you approach kind of chopping it up? Is there any synergy in having the same sizes?
Well, your application vector lengths can be enormous. They can be, you can have vectors of hundreds of thousands, millions of elements. And so, no one's going to build anything beyond 64K bits anyway, because that's the RISC-V vector length limit. But the way we envisage code being written, and this is what all the compilers are doing. Of course, humans can not do this. Humans can break this. But the way the architecture works is that there's an instruction vset-vl where you're setting the vector length. And let's presume I have a vector length of 100,000 elements. I would say in an instruction vset-vl 100,000, which I'm trying to set my vector length to 100,000 for this application. And the hardware will say, actually, I can't do 100,000. My hardware can only do 64 elements. And so internally, it sets the vector length to 64 and returns that back to software. And so software then gets a response saying, I couldn't set it to 100,000. I could only set it to 64. And so then the software writes a loop and subtracts 64 from 100,000 and iterates round this loop until the last iteration. And maybe in the last iteration, it's not actually a multiple of 64. It might be you're setting it to a value of 40. And so you do a vset-vl 40. The hardware says, I can do 40. Returns 40. You know you're finished. And there are elements beyond 40 up to, we said, 64. And those are called the tail elements. And then the V-type register determines what you do with those tail elements as well. So you might leave them undisturbed, or you might say it's agnostic, in which case I either clobber them with all ones or I destroy them in some way. But the user gets to choose what to do with the tail. But nevertheless, at the end of this software loop, you're finished your application vector length. So your application vector lengths, we presume, are going to be enormous. And as long as you're using a compiler or the human is writing it this way, you then have generated this vector-length-agnostic code. That code is portable. It will run, the same code will run on a machine from us of vector length 1,024 bits or 512 bits or 128 bits, whatever it is that you select. The same code will actually work. And the hardware, when it returns 64 in one instance, might return 32 in another. It might return 16 or 8 in another instance of the hardware. And you just iterate for more iterations of your software loop. And that's how the software and the compiler are meant to work. I'll say meant to work.
Okay, got it. All right, let's talk about matrix processing, matrix multiplication specifically. I know this is a huge part of AI maths in general. Tell me about the need to include matrix processing and how that affects your architectural decisions. And what about, vector versus matrix processing and the proportions of those? Like, how do you approach that problem?
Yeah, so there are multiple approaches for RISC-V. So I'll start off with the RISC-V international world. So there are 4 big approaches being proposed. There's batched dot product. This is a dot product instruction rather than a matrix multiply, but you can write software loops again and turn dot products into matrix multiplies. You can perform matrix multiplies with the dot product instruction. So one proposal is a batched dot product where it does up to 8 dot products in parallel. The number of elements that it's going to sum together in that dot product depend on the vector length. So for different implementations, it's going to sum together and reduce different numbers of elements. That's the first proposal. The second proposal is called IME, for integrated matrix extensions. This proposal puts the matrix inside the vector register. So a vector register, instead of just being a one-dimensional object, is now a two-dimensional object. It's holding a matrix. And so the source comes from a vector register. The destination goes back into a vector register, perhaps one of those grouped vector registers to make it even larger. So LMAL might be 2, 4, or 8. So that gives you more bits to store the matrix in. But IME always operates with the existing state. There's a few extra bits in V-type, but fundamentally it's working on what we already have. Another proposal is VME, for vector matrix extensions. And so this proposal takes source 1 and source 2 from the vector registers. They are vectors. And it does an outer product multiplication. Again, not a matrix multiply. This is an outer product. And produces a matrix result. those matrix results go in new state, new ISA state. That's the M part of the name VME. So it's vectors in, that's the V, matrix out, that's the M, so VME extensions. And that's what SiFive has in its high-end XM product. There's one further proposal in RISC-V, which is AME for the attached matrix extensions, where the sources come from matrix tiles. So there's a set of matrix tiles you can use as sources. And the destination goes into a matrix accumulator. Those are a different set of matrix registers that are used to store the result. And so this task group started off with the presumption that you may not have vectors available. And so everything they're doing has to be able to perform the standard vector type operations as well. So SiFive doesn't support AME because we have vector support in our processors already. We don't need that additional hardware in the matrix engine. So we don't do AME. We do VME on the high end. The batched up product are coming to all the standard vector machines as well. And IME, it's evolved from what SiFive had in the past. We had an early version, I would say, of IME, but the RISC-V International discussions have continued beyond where SiFive was. They have a more sophisticated approach now, in fact, for IME. But what SiFive will be supporting is this VME and batched up product. In terms of how I go about choosing, it depends how many matrix calculations does your algorithm need. And different algorithms need different numbers of matrix calculations. So if I look at LLMs even, do you think large language models, if I pick a large language model, 70 billion parameters, that's 70 billion max. That's a lot. But even in it, there are different phases. So there's the prefill phase, which is at the start where you're parsing the user input. So that's called the context, how many tokens the user has typed. It might be a small number, it might be a large number, and you're parsing all those tokens. That phase of LLMs is computationally bound. That's where you really want these large matrix engines to help you crunch those numbers. Once you've parsed all of the user input, you've generated something called the KV cache, and then you use that to generate the output tokens one token at a time. And because you're generating one token at a time on the output, in the decode phase, this is called the decode phase, it turns out that it's memory bandwidth bound. So suddenly the bottleneck is changed from computation bound to memory bandwidth bound. And in that case, the vector units themselves may be sufficient because it's not a computationally bound problem, it's a memory bandwidth bound problem. And so there's an example of somewhere where this mixed capability of having a matrix engine that you're using for the prefill phase, and then you're using the vector engines for the decode phase, and yet I'm running a single application. It's a single LLM, it's the same model. It shows the need that we need the matrix engine, we need the vector engine, and of course you need the scalar engine. There are some for loops that I mentioned earlier that you have to write, and that's what the scalar engine's doing. So you need this scalar vector matrix mix of computation.
I'm curious about what that AME profile, what's the use case for that AME profile, which is the matrix without any, if you haven't got any vector capability. I'm just curious.
Well, there are, it's a standalone AI engine. You can think of it like that. So if you have an existing processor and it doesn't have the vector capabilities already, then you can plug this AME engine in and use that, and all the computation can be performed on that. But we at SiFive are going to be doing VME because we have the vector units already. And so all the nonlinear activation functions, the softmax, top K, which is important now as well for MOEs, all of that type of computation is being done in the vector side of our XM processor, not in the matrix engine side. And so that all looks like vector processing to us. And so the vector units seem to be ideal to work on that workload.
What happens kind of at the compiler level or up in the software levels if software assumes one way of doing matmul and what the hardware wants to do is something else? Or tell me about how this is controlled. Yeah.
Well, how is this going to work? So RISC-V has 4 different approaches for matrix ops. How is this ever going to approach? Well, fundamentally, we're talking about loads and stores to get the title state in and out. So even when you have matrices in vector registers, they're two-dimensional objects. So the loads and stores are going to look different. So you need loads and stores, and you need the matrix multiply ops. That might just be a multiply add, a MAC. It might be a multiply subtract, but there's very few instructions we're talking about here. So it's load stores, MACs. And that's your ISA set that is supported by IME and VME. AME has all the other things that vectors would normally do, and batch.products just does a batch.product. It's just a single instruction. So fundamentally, we're looking at a very small number of opcodes. The presumption is software is written to support them all. That might be unrealistic, and it's not to do with the opcodes here. The opcodes, like we're saying, are 3 or 4 opcodes. It's not a lot of different opcodes. The problems are going to arise because the memory layouts may be different. And so the way data is arranged in memory for VME, IME, and batch.product might be fundamentally different. And so software that's written assuming VME, that you could have a library that falls back to batch.product, but the performance is going to drop because the memory organization is different. And so you're going to have to use perhaps slower loads and store operations to gather or scatter the data. So you may get lower throughput, but the hope is that the math libraries will support them all. And if they don't support them all, they support at least the current RVV standard plus whatever one acceleration format. So as long as they can fall back to RISC-V vectors, RVV standard 1.0, as long as they can fall back to that, everyone's hardware will work that has vectors. Yeah, that I'd say it's a hope. Again.
Okay, we hope so. One of the things you mentioned a few times was that these are proposed profiles.
Yeah.
But this is already what you've already implemented this, or this is already in your IP or already in hardware. I'm curious about how you actually work ahead of standardization, and how do you decide what's safe to put in the design or what to wait with?
Well, these designs have already taped out, so that they are in silicon. They are ahead, so that our customers understand that we're working at 0.7 version of a proposed standard. So we typically go relatively early to RVI, trying to get a standard around something that we've already implemented. But there are many, many potential different directions you can take. So other RISC-V vendors certainly look at what we're bringing into the RVI as a standard, and they have proposals that they might see are similar to what they're doing, and they want to put their spin on it as well. And so what's already baked in silicon is baked in silicon. There's nothing we can do about that now other than support it in software. So we are on the hook, SiFive is on the hook to support in the SiFive compiler toolchain the version of VME in this case that is already baked in silicon. I'd say the other vendors who've looked at it have been very supportive. There are minor differences, and it's to do with where the control bits are sitting. So the fundamental instructions haven't changed in this case, and so that's, as you're implementing something and working through and iterating through implementations, you tend to find where the bugs might be in your architecture. You tend to get those ironed out, and so we're coming in with something that has a proof of concept because it's in silicon. And so the standardization so far of VME has been around where we put the control bits. The fundamental operations haven't changed. But that's what we would expect just because we've gone through the process of building in hardware. So there is a risk, but luckily it's only been on the control side of VME.
Yeah, I guess the whole point is to kind of try and avoid fragmentation when it comes to software. But like you're saying, maybe it's worth it if we can move faster and get to hardware faster, right?
There's different markets as well. So this whole matrix fragmentation, like it sounds like batch.product, IME, VME, AME, is because RISC-V is going into so many different markets. And when you're going into the edge, the far edge, like you mentioned earlier, there's just not a lot of silicon area available to put large matrix engines down. So you are going to be doing the computation in vectors, and then that sort of drives you towards IME or batch dot product, that you don't want to add the extra state. And then when you are going into data centers and throughput is more important than silicon area, you have to keep up with the throughput. You're going to throw the extra silicon area down, so VME or potentially AME are going to make more sense. So the fragmentation makes sense because they are fundamentally different markets. And RISC-V's already done that. It has the 32-bit standard and the 64-bit standard. And now there's RBA23, RBB23. So there are different versions or different amounts of RISC-V that you might want to pick up for different market segments. So yeah.
That makes sense.
The other thing would be the data type support. And so at the edge, it might be that you only want to support int8, maybe the new FP8 formats, or even smaller, there's FP4 and surprisingly a 6-bit format as well, FP6. You might not want to support FP32 or FP64. Certainly FP64 could be very large. Supercomputers might want FP64, but even AI data centers, FP64 throughput has actually dropped recently. If you look at the performance of the data center for FP64 is getting lower and lower because more and more support is being added for smaller data types, and the focus is more on the smaller data types. And so I would also say that would be a difference as well as you're going towards the edge markets. It's smaller data types need to be supported. And then if you're training models, FP32, bfloat16 are typically what used to train models, but for inference, smaller data types. So I see that difference as well.
I mean, these data types are constantly evolving now as well. I mean, they change.
Yeah, they do.
How do you keep up with that in hardware as well, right?
At lower throughput is the honest answer. So you can, for smaller data types, the advantage is there's not a lot of possible combinations. So for 4-bit data types, there's only 16 different values. So you can build a lookup table and you can just do the conversions through lookup tables to a supported data type. So for 4-bit, we can convert to FP8 and we just fundamentally support the FP8 format in hardware. For different 8-bit types, we could do something similar. It's only 256 values. You can do a lookup table. So for the smaller ones, go invent all day long because we can convert with lookup tables. Now that means we're not running at the full throughput of a 4-bit piece of hardware. A 4-bit piece of hardware, you might presume you get twice the throughput of 8 bits. But if we're converting from 4 bits to 8 bits in the SiFive hardware, you're only going to get the 8-bit throughput on the 4-bit data type. There are still advantages because you only need to load half as much data. The data bandwidth requirement is halved and the data storage requirement is halved. So you get all of those benefits. And for the decode phase, where it's bandwidth limited, you will see a performance improvement, but in the prefill phase, where it's computationally bound, you would not see any benefit for the 4-bit data types over the 8-bit data types. But at least we can support those as long as we can fundamentally handle something like 4-bit. And so that's an interesting question. What do you do with something like 6-bit, or if they invent a 7-bit, how do we handle that? And if we don't have the fundamental support to be able to decode 6 bits into a wider data type, you're going to be doing lots of bit shifting. So your performance in those cases would drop significantly. So really, as long as the data type variation is happening with supported widths and not inventing a new width, we're okay, I would claim. And when FP5 comes out or FP3, our performance is going to drop significantly because we just fundamentally don't support that without lots of bit shifts. So your performance is going to drop in those cases.
I mean, everybody seems to have their own FP8 format, and I know you guys support OCP FP8.
That's correct.
Tell me about why you picked that one and how widely is that one being used, for example?
There's actually multiple versions even of OCP.
Of OCP, okay.
FP8. But we support both. So our hardware supports both. So the exponent width of your floating point number can vary. It can be a 5-bit exponent or a 4-bit exponent. That both of those are part of the OCP format. We support both, and in fact, you can mix 4-bit with 5-bit in the instructions. We allow mixed precision there as well. Why did we pick the OCP format? Because it was standardized ahead of IEEE. IEEE is coming along behind OCP. IEEE is different. It has yet another format. It has a exponent width of 3 bits. So there's 3, 4, and 5 width of exponents in IEEE, and the bias is different, and the infinities and nans are different. So there are some differences with IEEE, but it's coming later. And so what we see out there is that models are being built that match the hardware that already exists. And so there's already hardware, our friends at NVIDIA have already built hardware that has the OCP format supported. And so models are being built today with OCP. And so we are supporting OCP because we see the models are there. IEEE will get there. We know our friends there will get there. They will standardize, and we will have to support the IEEE FP8 format as well. Now, that brings us back to that V-type register where I said the vector instructions don't encode the operand width. So it's just, I want to do, in this case, a floating point vector add. So VF add. And what width is my data? That's encoded in the V-type register. And so there's additional bits that have been added to the V-type register to indicate that I am either OCP, exponent width 5, exponent width 4, or in the future IEEE, and one of the 3 different exponent widths, or potentially others. So there's additional bits being added into the V-type register. So when we do encode an instruction, that is vector, floating add, VF add, the V-type says, hey, it's one of these different types. Now, if in the future you attempt to run that model on us, we wouldn't support that without conversion. So if you just took the binary, we would see the V-type is set to something we didn't support. That would be an illegal instruction. We would see that before we even attempted to execute it. We could attempt to handle it by doing a conversion of the IEEE FP8 over to something else potentially larger, like FP16 or a bfloat16, and then returning, executing it, and then converting it back into the format that you want it. We could handle it, but again, performance is going to be lower.
I really must ask you about memory. We're used to hearing on this show that certain types of workloads are memory bound or memory bandwidth bound, and that this data transfer to and from memory is so crucial for performance overall. You mentioned queuing earlier, so I want to pick up on that. Tell us a bit more about the tricks that you can use in the kind of memory area to try and keep that latency as low as possible.
Yeah, well, our processors have 2 paths to memory, fundamentally 2 wide paths to memory. There's the standard memory interface that goes through all the caching hierarchies. That's traditional CPU. That works great if you're running the type of workload that can fit in a cache. And we continue to have that. There are many workloads that fit in a cache. But if we again come back to the AI world, these model sizes are enormous. So if I mentioned earlier, 70 billion parameter model at 70 gigabytes, you can't have a cache of 70 gigabytes. That's ridiculous. So what do? We can't cache it. It just won't fit. So you're going to be streaming it through. So we have another wide interface, a low latency, high bandwidth interface that is not cached. It doesn't even attempt to cache the data. And the way our processor works, the vector unit, like I said, is post-commit. So our vector unit sitting post-commit, the instructions execute, all instructions go through the scalar unit. When they're committed, if they're vectors, they're queued up in a vector command queue to be executed later. When we see a load going through, we start that load. We send that request off to the external memory system, uncached in the case of AI models, which have large data sets. And then that response will come back to these queues that I mentioned, this vector load data queue. The response might come back out of order. You might have different memory hierarchies in your SoC. You might have some onboard memory, some offboard memory. You might have chiplets, and you have to go chiplet to chiplet for some addresses. So we can cope with the responses coming back out of order. We put everything back in order. And the goal is that the queue depth matches the latency that we're trying to cover. And so the first load that goes out, we can't do much. If the first instruction you execute is a vector load, we're going to see that memory latency. We can't really hide that. But every single vector load that happens after the first one, After you first switch on first thing in the morning, you haven't had your coffee yet, it's slow. But every other vector load after that one is going to be hidden. The latency is going to be hidden behind that first vector load. Those future vector loads, those subsequent vector loads are coming back into the vector load queue. And when the vector load eventually goes to be executed, we're expecting the data to be in that queue. We just pop it out of the queue and write it back to the vector register file. And if the next instruction used the vector register that had just been loaded, the vector load to use is 1 cycle, which is phenomenal. If your memory latency happens to be something large, 200 cycles or more, we are getting the effective throughput of vector load to use of 1 cycle. That queue size is large. If you're trying to hide very large memory latencies, that queue size grows and grows. So it is tuned, that vector queue depth is tuned for different SOCs. So when customers come to SiFive, they work with us, they tell us what their external memory latencies are, and we tune that length so that it matches what they need. Yeah, it's more complicated than just the memory latency. You have to look at the number of load instructions versus the number of computation instructions. So arithmetic intensity comes into it as well. There's all sorts of calculations, but we do size it for different customers. And that's the way SiFive tolerates memory latency. I know GPUs do it a different way. They have multiple threads and they context switch continuously. So they use SIMT and they switch threads. We think that multiple threads is going to have an even larger area than these queues. So we believe the queues are smaller than having multiple threads. In this case, let's say 200 threads worth of registers, both scalar and vector registers to switch. So queues are smaller. That's why we're doing it that way. And it's a traditional CPU as well. And it's one ISA that does the number crunching as well as the application processing. It's all one ISA. So that's why SiFive's doing it this way.
Got it. Going to ask you about what you are planning to do or what's coming up in the future. We mentioned kind of the differences between the prefill stage and the decode stage, for example, but what kind of workload changes or new workloads are influencing how you architect for the next generation of intelligence cores?
Yeah, so you've covered some of that so it's data types, it's sparsity, and it's mixture of experts. So These are the things that are coming. So data types, they're just coming up all the time. So we've covered that. Sparsity, we want to handle more than just structured sparsity. So we see others out there have structured sparsity. You have to have exactly 2 elements in every 4. We're looking at having something that's more flexible than that. If you look at RISC-V vectors, that they already have the concept of mask. So you have a mask field, it's in another vector register, and you can switch individual elements on and off. And it would be great if we could handle that type of thing, not just in vector math, but also in matrix math, if there was a way to do that. So that's something that we're looking at. And then for MOEs are great in that you don't have to do as much computation. You don't have to load as much data. So they bring this wonderful benefit. The downside is that you can't batch the decode phase. So one little trick that people have played is in the decode phase where you're generating 1 token at a time, instead of generating 1 token at a time, let's generate multiple tokens and you batch it together. So you only have to read the weights once. With mixture of experts, the downside is that you might have different experts being required within a batch. So suddenly that falls down. So you really have to support the batch size of 1. So that's the downside of mixture of experts. And then there is a phase where you have to pick which expert you want. And so different algorithms there for picking which expert. Top K is a common one. And so some hardware acceleration around top K can help. And then, of course, there's all the other hardware acceleration that I briefly mentioned before, but all the nonlinear activation functions, softmax, layer norm, those are things that need acceleration as well. And so SiFive has hardware pipelined exponential units that can help with the nonlinear activation functions and softmax. And RISC-V, as standard, has a reciprocal square root to 7 bits of precision, but you can iterate on that. And that helps with the norm functions, so layer norm. for instance, can be sped up with that. So there's lots of acceleration for AI models. There's lots of interest for AI models. But there are other workloads that we're looking at as well, where you can put in dedicated processing. So SiFive has also had the capability for customers to add their own acceleration functions. So we call it VCIX, V6 for vector coprocessor extensions. So you can add your own custom opcodes. And so we do have customers using that. A lot of customers use that to, in fact, attach their own proprietary matrix multipliers to come to us. They have their own standalone accelerator. It's not AME in that it doesn't have any of the vector part, it just does the matrix part, and they need everything else. They need all the vector computation, and they come to us and we just attach it onto the V6. We have a scalar coprocessor interface as well, that's new. So you can attach things to the scalar side as well. The scalar side is useful where you need to make control decisions, and the vector part obviously is for data throughput.
I actually think that's the perfect place to finish. John, thank you so much for a fascinating conversation. I certainly learned a lot. Thank you very much.
Hey, Sally, thank you very much. I've told you before, but I've followed you for ages, so this has been a real pleasure.
Thank you very much, John. I learned such a lot about vector and matrix processing and RISC-V. This episode of AI with Sally was brought to you by SiFive. Thank you very much, SiFive, for sponsoring us. If you want to learn more about SiFive, please check the links on the podcast page at eetimes.com. That brings us to the end of the episode. Please tune in again next time for more conversations around AI silicon and systems. If you're listening to this on the podcast page at eetimes.com, links to articles on topics we've discussed are shown on your left. AI with Sally is brought to you by Aspen Core Media. The host is Sally Ward-Foxton, our project manager is Colleen Heckman, and the producer is James Eade. Thank you for listening.